All right, thanks, Nick. Yeah, so what I want to do today is show you some data from ICON. So ICON's been in space for about a year now. We have a little under a year of data. I'm gonna, out of everything, I'm gonna pick on one science topic to show you a little bit of a range of data and hopefully get into one of the questions that we posed back when we were coming up with the mission. And that specifically is going to be looking at these large-scale waves, these tides, and how they change composition in the upper atmosphere, what that can do to the density of the ionosphere. I know we have students watching this and watching the recording, so I'll introduce these terms. I'll spend a bit of time to start going over some of the basics, then we'll build up and we'll get to the science that we're seeing. Oh, I'm on the wrong screen. There we go. So what will I do? I'm going to spend a bunch of time talking about the middle thermosphere, so I'll sort of introduce that. Then we'll look at the ionosphere, low latitudes. We'll look then at the kind of questions that motivated the ICON mission, and that's going to be important for giving some context to what I'm going to show. Show the progress that we managed to make with the timed spacecraft and its data, and then we'll get to you know what the new ICON data set's telling us about this problem. So I like to start with a big picture. So start looking at the sun, okay, and start looking at solar, the light coming from the sun. And you know, people have seen this before a million times, but it's worth thinking it through. We get obviously most of the light in terms of radiative power from the sun in sort of the near UV, the visible, the infrared. This is all coming from the photosphere, and it really doesn't change very much one day to the next. When we get to the short wavelength emissions that are coming from the sun, especially as we get into this region, the extreme UV, so wavelengths kind of shorter than about Lyman alpha, we get a couple of things. So suddenly it's not looking like a black body curve. What we've got is a set of bright emission features, and a lot of variability between solar min, solar max, right? Sometimes factor of 2, factor of 10 even at some of these lines. And it's this really variable EUV that I think sort of starts our story. And we ask, so what happens to this extremely variable radiation coming off the sun? And of course, it flies through space and it reaches the Earth, right? But what happens if we look at more detail? You see these panels on the right show two kind of views of the same sort of thing. Looking at where does this light get absorbed as a function of wavelength? And obviously, right, the visible light pretty much makes it to the ground almost uninhibited. You get into the sort of mid UV, and you get this region here that's being stopped in the middle atmosphere by the ozone layer. Get out to the far, and especially this extreme UV, this highly variable flux off the sun. And this is almost exclusively being absorbed in the Earth's upper atmosphere. So starting from around 100 kilometers and up, a lot of it being absorbed near 150, 200, and some even absorbed at higher altitudes. And if we think about the wavelengths that we're talking about here, these are pretty short wavelength photons, below about 1,000 angstroms or 100 nanometers, whichever you want to use. And so these individual photons have a lot of energy, and they don't just get absorbed by the particles, the oxygen, the nitrogen, things that are in the upper atmosphere. But they've got enough energy, they exceed these ionization thresholds marked in this bottom panel. And so, if I hit an oxygen atom with something at 30 nanometers, it doesn't just absorb it, it breaks that oxygen atom apart, and ionizes it. And so I'm going to spend time looking at this middle thermosphere, which is sort of a funny name for, I think, a really interesting region. So if you look at the plot on the right, it's temperature versus altitude in the atmosphere, right? We've got our lower thermosphere, mesopause lower thermospheres usually clumped together, this super cold region. And our upper thermosphere is sitting off here. It's really hot. but it's kind of isothermal with altitude. And the middle thermosphere is this region here with this really rapid temperature rise. And part of that is because it's absorbing a lot of this EUV. We have very low density in this region. I said, because of the short wavelengths involved in what's being absorbed in this region, we get a lot of ionization produced here. So very high ionization rate. And a byproduct of that isn't just that we're producing ions and electrons that sit there, but some of these electrons produced in this way can have a bit of extra energy, and this leads to one of the forms of airglow, and we'll introduce what that is in just a little bit. And another thing that characterizes the middle thermosphere and up, really, is that we've got above the region where the atmosphere is very well mixed, and so we can start to have changes in composition between different locations, both as a function of height and also, latitude, longitude, in a way that we don't get, in the lower atmosphere, where the composition, at least in the major species, is pretty solid. So, taking another look at that ionization, right? We're looking at these short wavelengths getting absorbed by atoms and molecules. I drew this fabulous cartoon on the right-hand side. So I've got an EUV photon, it hits an oxygen, and it has enough energy to break it apart and create an oxygen ion and an electron. But if its wavelength is any shorter than this ionization threshold, then there's extra energy in here. And that extra energy can go into a couple of places. Maybe what we'll get is an O+ that's not in its ground state. Maybe that'll be an excited state ion. Or, what often happens is this electron carries away a bunch of kinetic energy and goes speeding off. And then that electron has some energy and can go collide with other things, other atoms and molecules around it, and excite those. And so the reason that's important for what we're going to look at is it leads to these, it's one of the ways we lead to this process called airglow. So airglow happens, various layers of the atmosphere. And what's happening is that when we're getting atoms, molecules, ions in excited states, if that happened in the air in this room, at least I'm in, what typically happens is that atom or molecule will collide with something else pretty quickly and lose that extra energy through collisions. By the time we get up to the upper atmosphere, starting maybe around the mesopause and up, those collisions become less frequent. And so that atom or molecule in its excited state might de-excite by emitting a photon, which usually takes some time. It usually needs some time between collisions before it can do that. And so we get this phenomena of airglow. And there's various things that can produce these excited states, chemical processes, ionization, photoelectrons that we just saw, recombining of ions and electrons. And so throughout the thermosphere, and especially in this middle thermosphere, we get a bunch of these airglow emissions. And not all, but many of them are related to those photoelectrons being produced by a lot of this EUV being absorbed. We'll get airglow in infrared, visible, ultraviolet. The color often has some information about what atmospheric or ionospheric species is emitting. If you can pull out Doppler shifts in that, you can get to wind. Sometimes shapes of emission features can get you temperature. Maybe the brightness can tell you about density. So there's a lot of information there. If there's a process that's causing that excitation. If we look at this picture on the right, this is a photo taken from the space station. And it's clearly at nighttime. Otherwise, the Earth would be extremely bright. And you can see some of these airglow layers. You can see there's a green layer here that's bright around 90 to 100 kilometers at night, and a red layer up in the 200 and something kilometer range. If we could take the same picture in the day, which with a regular camera, the Earth would be too bright, but if I kind of blocked out the Earth and took this picture in the day, there'd be other airglow features filling up this gap in between these, so filling up that sort of middle thermosphere altitude region. And that's because some of these features get produced by those photoelectrons.
If we're in sunlight, we have a lot of those being produced. And if we're in darkness, we have very few of those. To understand some of what I'm going to present when we get into the data and the nuances of it, we need to understand just two types of airglow in the far UV that we'll dive a little deeper into. And those are going to be 1356 and LBH. So these are associated with either atomic oxygen and molecular nitrogen. And principally in daytime, these are both generated in a similar sort of way, where we have photoelectrons either hitting a nitrogen molecule and producing LBH, or hitting an oxygen atom producing 1356. And as it happens, we get a lot of this emission coming from that middle thermosphere region, in part because of the abundance of the photoelectrons, and also as we get lower in altitude, there's some absorption of these features. So it really gives us a window into by measuring the two, it gives us a window into the composition of this region. During the nighttime, there's another process that dominates. And it'll only produce this 1356. But what we have is some O+ ions. And if they find an electron and recombine, we can get an oxygen in an excited state. It can emit light at that same wavelength. And so at night, we often use this as a way of measuring the ionospheric O+. And if we take a picture or build up an image, on the right, this is from gold, looking at 1356. And this neatly captures what we've just talked about. So on the left-hand side, we have a region of the Earth that's in sunlight, and we're seeing a bright emission pretty much covering the whole of the daytime. And that is photoelectrons hitting atomic oxygen. And you come into the night, and then what we see is an emission that looks quite different spatially, right? It's structured. It follows the magnetic equator. This is the low latitude ionospheric O+. And, there's some aurora up near the northern part of the image. It's the same oxygen. The excitation process in that case is from high energy particles hitting the oxygen. But this sort of captures everything in one. Okay. So 2 slides, I think, on the ionosphere, just to give us what we need. So these EUV photons are not just creating those nice photoelectrons, right? They're creating the ionosphere. And if we look on the right-hand side, in the top panel, where are we producing ions? What as a function of altitude? Then we'll see that we have a strong production, kind of a peak in production in this middle thermosphere region, let's say about 160, 170 kilometers or so, with a lot of ions getting produced there. And there's another peak down in the lower thermosphere that's going to be less important to our talk. But this should be no surprise. This is where we're seeing a lot of these photoelectrons being produced. It's where we're seeing these far UV air glow being strong. Right? It's no coincidence these are all in the same altitude range. Well, if I go look, where are the most abundant ion densities, I get a plot like this. I'd say this is for mid-latitudes. Low latitudes is fairly similar. And I get a peak, an O+ peak, what we call the F layer, maybe 250, 300, even higher. So much, much, much higher in altitude than this peak in production rate. And so what's going on here? Well, obviously production's not everything. We need to think about loss and transport as well. And sure enough, loss is strongest on at the lower altitudes where the atmosphere is more dense. The main loss for O+ is through collisions with species like N2. So the more dense the atmosphere is, the more quickly it'll be lost. So you'd expect some skewing of this. But that's not all. It's that other term there, that transport term, that you really need to understand this picture. And if we look at the low latitude ionosphere, we get a picture like this. So over on the left-hand side is a little diagram of the E region dynamo. So in that lower level of the ionosphere, we have pretty dense atmosphere and ions, and so we get a lot of collisions between them. And so with the wind patterns blowing, the ions will feel a force from the collisions with the neutrals and want to move too. The electrons have a much smaller collision cross-section, so they pretty much can ignore the fact that the wind is blowing. So I can create a motion of the ions relative to the electrons, which gives me a current. And if I have gradients in the wind or gradients in the conductivity, I can build up electric fields, which predominantly in the daytime gives me an electric field at low latitude that points eastwards. And that will map up along the field lines up to that middle thermosphere and higher altitudes. And there they'll see an eastward electric field and kind of a northward magnetic field. And it produces this transport, this motion of the plasma in the direction E cross B, which is sort of upwards and outwards. You can kind of see by these green arrows. And so my ions might be being produced down here most strongly, let's say at 160, 170 kilometers, but they're being moved upwards and to higher latitudes. And then they're free to move parallel to B through pressure and density, and build up these two regions of dense plasma either side of the magnetic field equator. I can measure that uplift in a statistical sense. This is data from a radar at the magnetic equator. I can put it into a model, produce an estimate of these two bands of plasma, and I can go image this, right? This is the same gold image that I had before. And this is sort of why we see, instead of the peak concentration in the ions being at the geographic equator or even following the magnetic equator, being just either side of it, it's the result of this upward motion, this transport effect. Okay. So what were we thinking of when we put ICON together? Well, we had a few questions in mind. One of them was related to this. And so to put it in context, yes, I started working on ICON in about 2009 or so. So, you know, think of questions we were thinking of then. And we were looking at this structure. So if you take an instantaneous snapshot of that low latitude ionosphere, what you'll see is a signature totally dominated by where is day, where is night, where is my production maximizing. But if you instead control for that and build up an image at a constant local time, in this case just after sunset, and map its structure here shown on the right from two different instruments, you see this kind of structure to it. So it follows the magnetic equator for sure, but there's a longitudinal asymmetry in it. We termed the wave 4 pattern, right? So these 4 peaks, where it gets a bit brighter and moves a bit further from the magnetic equator. And we'd see this much of the time, most of the year, not all the year. There's some seasonal patterns and things in here. And we were looking at, well, what's creating this? Okay. And it's pretty clear it's not fluctuations in solar EUV that somehow match the Earth's rotation rate. This is something going on internal to the Earth's atmosphere and ionosphere. And you know, the answer we were drawn to pretty quickly had to do with non-migrating atmospheric tides. So very large global scale wave patterns that get generated in the lower atmosphere through a longitudinal asymmetry in the energy inputs. So the most likely candidate being a sort of longitudinal asymmetry in latent heat released as water vapor turns into water droplets, which occurs across this sort of broad altitude range. And so we have this combination of energy being put in, and it has some spatial structure, both in longitude and in altitude. And then to add to that, it's also periodic with about a 24-hour cycle, right? This is all related, of course, to solar heating in the lower atmosphere. And you add those 3 ingredients together, and what you get out is these tides, so waves at 12 and 24 hours that reflect in a fixed local time frame this wave 4 structure. And we'd been able to go measure these as they kind of get up into the upper atmosphere. So the top plot here was showing some of the wavefall pattern we were seeing in SABRE data at about where it runs out around 110 kilometers or so, where we get temperatures up to. This is showing latitude, longitude at a fixed local time. You see that wavefall structure. And then we could also see with CHAMP, way up at 400 kilometers, same sort of wavefall structure in the wind fields at those altitudes, suggesting these waves generated in the lower atmosphere come all the way up through the thermosphere. And this was great. And we built up this picture, and we could see these wave patterns varying with season. And we'd see a corresponding variation in the ionosphere that sort of matched that seasonal view. So it became pretty clear that we understood these waves are what's causing this structuring. What wasn't quite clear was what was this mechanism, how, right? Because we had good observations up to kind of just below this dynamo region. And then some observations high up, and we were missing some of the observations in this region throughout some of the dynamo region, throughout this middle thermosphere where we think these ions are being produced, where we think they're being transported. And really trying to unpick that mechanism was something we were trying to get at with ICON. Well, of course, you don't stop there, right? Plenty of people were looking at this and trying to understand if the data that we had could point to things, maybe combinations of data and models could narrow things down. And we made a pretty convincing case of what's going on is that these tides are varying that E-region dynamo picture that we showed before. We're varying the winds, can vary the electric fields, could vary the uplift, could vary the transport term. And we could get data like this. On the left-hand side, these are some measurements of that upward drift velocity. I think these are from RockSat-1, showing if you control for local time, showing kind of a four-peak structure. We couldn't quite measure the electric field at the E-region directly, but we could get a proxy for it. This is to do with the strength of the equatorial electrojet, which is a strong current system flowing, I guess, in the lower E-region near the magnetic equator. And again, seeing it responding to this longitudinal structure. So we could take that magnitude of that change in the uplift, put it into a model of the ionosphere, and say, hey, well, what happens to my O+? Recompute the airglow, and it matched the observations pretty well. And so we had a pretty convincing case that problem solved. Okay. And the problem was that while that all hung together, there were other good candidates for the mechanism that maybe weren't the main thing going on, but could be playing a big part. We just didn't know. And I came up with this list around that time, it's been a while, looking at 5 plausible candidates. Okay, so the E-region dynamo we've talked about. There's another process called the F-region dynamo. And we said, well, what can we modify that? And that could play some role. Okay. We looked at changing the total mass density of the thermosphere. That seemed pretty unlikely. Maybe plays a very, very tiny role. We see that these winds associated with these tides make it all the way up to the altitudes of the F-region ionosphere. So could they be advecting the plasma or causing some motion of it? And there was this final one that, what about changes in the thermospheric composition, especially this ratio of oxygen to nitrogen in and around that region where we're producing a bunch of the plasma? Because if we're producing O+, the more oxygen that's around, that's going to help with O+ production. And the main loss mechanism for O+ is collisions with N2. So this O to N2 ratio can impart some effect on the ion densities. And it's this third one again, it's probably not the main process. I mean, I think we're pretty well established the E-region dynamo is the main process, but does this play a part or not? Let's go and try and answer that. So you can go and run a model. I think this is time GCM simulation on the right-hand side. And look at what the models say. So the models can simulate these tides moving up through the thermosphere. And sure enough, you could see, you know, a sort of a wave force structure in the perturbation of this ratio, this O to N2. So we're not looking at its absolute value, we're looking at its perturbations with longitude. And in the middle thermosphere, you know, the model might estimate they're around 3–4% kind of changes. And you can understand at some basic level why might this be happening? Why is a wave in the atmosphere causing a change in composition? And you can get some way there by looking at this linearized continuity equation at the bottom. So if I look at the change for any one species associated with a simple wave perturbation, I'll find it has two terms in there. One is to do with compression and expansion, you know, divergence of the horizontal flow, and that is going to affect everything equally. But there's this vertical advection term, so it's related to the vertical wind component of the tides, and that'll affect things a little differently because each species has a different scale height, this value h here, and so that vertical wind is not equal on all species, and so you can kind of see, you know, it's simplifying some of it, but you can see from that equation why you might intuitively expect a large-scale wave that has some vertical wind associated with it to create a variation in the composition in this region. Not terribly strong, but still. We can do better, right? We can go make observations. I said we've got this airglow that gives us a window into the oxygen and the nitrogen. And we use data from GUVI on timed, and went look at this. This is some data from summer of 2009. And if you look in this northern sort of lowish latitude region, you can see a spatial structuring in the O to N2 that looks a lot like this wave-4 pattern we've been looking for. And I put that into my model and ran it through and said, well, you know, that's not going to produce the whole variation in the ionosphere that we see, but it could produce as much as a third of what we see. So this could be a 30-something% effect that we're looking at here, which I'd want to get right. Not the primary candidate, but if it is a third of everything going on, I want to understand that. There's a problem. There's always a problem. The problem came when some folks went and dug data deeper into this data that we'd looked at with timed. So the figure on the left is the figure I just showed you, but all panels of it. And over on the right-hand side is another look at the GUVI data, looking specifically at the oxygen, this 1356, breaking it out by altitude. And what they noticed was that this wave-4 pattern is there up at the high altitudes, and it's really not there down at the low altitudes, down in this middle thermosphere region, this region where we're expecting to see the composition variation. And they went further and pretty much showed, hey, you know, it looks very convincingly like in situ measured ion densities at these altitudes. And the conclusion at that time, I think was pretty good, was that this wave-4 pattern we were seeing here isn't really the O to N2 varying. It's really that minor contribution from O+. Remember that the 1356 has this daytide photoelectron hitting an oxygen, but it also has this O+ meeting an electron recombining. It's dominant at night, it's minor in the day, but at these couple of percent levels, it can make a big difference. Okay, and that's, you know, that's where we got to with that, and that was a convincing explanation as to why we didn't have case closed. And I want to revisit that today. I know I spent a long time introducing it, but that's because I'm revisiting this problem. And I want to come back to it with the icon data for a couple of reasons. So one is I think we may have picked an unfavorable local time when we were looking at the GUVI data. But also the icon's giving us a whole bunch of stuff. We've got the O2N2. We can measure it in the same sort of way as GUVI does. We can also get the O+ remotely sensed, down there in the region where it would be giving us the contaminating signal. We can get the winds blowing all the way up in the middle thermosphere during the daytime, and some other stuff. So I want to tie all that together and say, does this idea hold when I look at it more carefully and with more data? Okay. So here's a artist rendition of ICON. Carries 4 instruments. One of them measures the ion velocity. It's trying to get that uplift. I'm not going to show data from that today. I could, but in the interest of time, I'm going to focus on the remote sensing data. So this is making measurements off on the limb and actually just a little below the limb. In infrared, we use that to get atmospheric temperature. We measure Doppler shift, we can get wind velocities. And in a few emissions in the far and extreme UV, we can get at this composition in the neutrals and this O+ abundance. Okay, when am I going to look? So I have a little less than a year of data so far, and I've focused in so far on sort of March and April of this year. Why? Because some of these tides that produce this wavefall pattern have a little seasonal peak around that time. Here I am looking at data from the MIDI instrument that measures temperatures and winds. I'm looking in the 97 kilometers, so maybe the very bottom of the thermosphere. And if I look there, then I've got data day and night continuously. So in temperature and wind, so I can do a full decomposition, and I can look for 2 tides in particular, DE3 and SE2. They both have a wave force structure. They both are seen to move eastwards, and they have slightly different periods. And I'm going to focus in on this latitude band about 25 to 35 north, similar to where we did with GUVI. I'm going to stay away from the magnetic equator as much as I can reasonably, while still having strong tide signature to look at. And so if I look at these and I look at like the zonal wind, up at 30 north or so, it's pretty strong in D3. There's definitely some SE2 signature there as well. And the meridional winds and the temperature show up a little further south. But I've got some tides. I can look higher as well. I don't get a full diurnal cycle if I do. So some of the airglow that comes at higher altitudes is only there in the day when I have processes like these photoelectrons present. But I can make wind measurements at 150 kilometers during daylight hours. And I can look for the wavefall pattern. I can't formally decompose it fully, but I can look at how its phase changes with local time. So here we're just showing longitude, local time in this latitude box at 150 kilometers. And we see this eastward motion with time. And I can look for a best fit rate of motion. And it falls somewhere between what I'd expect for the 2 tides that I think are present, D2, SE3. So it's consistent with the idea that I've got both of them present. And so when I do this kind of analysis and I just pick out one, I get a best fit line that falls slightly between their rates. But the structure is moving east with time all throughout the day. Okay. What do I see in my composition data? And I broke these up into ascending and descending nodes, and I didn't label them. One of these is ascending node, one of them's descending node. And I did that because we sampled the same local time at a different day of year
with those two, and I didn't want to mix the day of year variations with the local time variations. So both of these run day of year on the vertical axis, longitude on the horizontal axis. Local time runs the opposite way to day of year, so it increases as you go downwards. And in both of these, I see a strong wavefall pattern, especially with this one on the right-hand side that sort of falls in the time range when D3 is particularly strong. I see it move eastwards, maybe up until about noon, matching about the rate I'd expect for D3, and then something complex happens in the afternoon. And if I look at this other one, you could kind of convince yourself you could fit something moving eastwards up till about noon, give or take. It's a little more messy. And then in the afternoon hours, the signal looks to be moving west or east. It's doing something much more complicated. So at first glance, I get not much further than I did with Goovy, but maybe I'm seeing the signal in the morning. And can I go flesh this out? Can I convince myself any better than this? Well, I can go measure the O+ and look for its wavefall patterns as well. This is with a different instrument. It sees to a slightly different location, so the day of years are a little different. But I can look at either the peak density, NMF2, or I can look at the whole column of O+ that we're measuring. And with both of these, again, increasing local time runs downwards. And we can see in the morning hours, very little pattern at all. And then starting around noon or so, a real pickup in the amplitude of the wavefall signal, consistent with there being more O+, because we've had that time to build up more and more ionosphere, more and more production going on. And this shows the signal moving eastwards, but if this is not quite at the same phase as the signal in this, you can imagine how when you add them together, you get this confused signal in the afternoon hours because of this stronger O+ that's present. And we can do a bit more. We can do a bit more by looking at this a different way. So instead of taking weeks of data, throwing it all together, throwing it through something like an FFT and trying to pull out the tidal signatures, we can try look for stuff going on an orbit by orbit basis even. There's a few plots here, so I'll take a couple of minutes to walk through these, but this is one orbit, this is one channel of the mighty instrument. And on the left-hand side, these two here show the winds that we're observing in the green line and the red line. So they measure at slightly different altitudes. They have some overlap. And throughout sort of the middle thermosphere and coming up into the upper thermosphere, we see this. It's pretty strong, positive, negative. In this case, we see them as descending layers in the wind. And there's a mixture of things going on here, right? This is not just a function of local time. We're also moving in latitude across here. But we're crossing through these tidal phase fronts and seeing them in this view. Because there's a bit of a mix of local time and latitude, I wouldn't go pull out and say, I know exactly which tide I'm seeing where. But this is the signature we expect. But we measure more than just the wind, right? We get the wind from the Doppler shift of this emission, green and red in this case. We also get the brightness as a byproduct. It's not what we're optimized for, but you see how bright that is. And so here in these panels here, I'm looking at the green line, and the top panel is a simulation, which sort of says, what do I expect to see? So I expect to see a bright layer in the lower thermosphere. It's kind of dominated by some production mechanism. And I expect to see another layer that sort of fills the middle thermosphere. And then there's another layer in the upper thermosphere as well. And if I look at the observations, I see this. And there's a little bit of contamination on the very left-hand side as we're coming out of the South Atlantic anomaly. We get clear of that, and we see, kind of the same general structure, but there's some perturbations in here. I can see it get dimmer, brighter, maybe dimmer, maybe brighter out here. So if I take this brightness data and I detrend it, I get this picture over here. And again, I see these sort of descending features, right? There's positives and negatives. But this is the brightness of the emission. It's not the Doppler shift of the emission. If I go look, this panel at the bottom repeats that one. So it's the winds. What I've done is put little black dots where I get wind reversals in the horizontal wind. And if I overlay them on top of the brightness, I can see that the peaks and troughs in the brightness kind of lie up with the wind reversals in the horizontal wind, which would all make sense if we're seeing tides, and it's going to be the vertical winds and where they're maximizing, which is going to be right here as we're transitioning the sign of the horizontal wind, perturbing the oxygen that's producing this this emission brightness. So it gave me an idea of going and looking at the green line brightness, and right there in the region where we're trying to measure the O2N2. So in this case, 150 to 160 kilometers, so maybe a few kilometers below, but still. And pull out its wave 4 pattern. I separated the instruments here, and hey presto, we see there's wave 4 eastward moving features perturbing the green line layer, which is you know, and there's some different rates in here. There's probably evidence of D3 and SE2, but you know, maybe this is not being affected by the O+ recombination in the way that our far UV is. And I'm really saying, yeah, you know, I think we understand what we're seeing, which is we expect to see this composition variations. We think pretty convincingly we are in the morning if we stay away from where the O+ density is the strongest. The picture gets complicated in the afternoon, and we'll need to do more to sort of pull apart these signals. The green line brightness variations really says nothing has changed in the afternoon, except those O+ ions coming in and complicating things. If we sort of extrapolate from this, we can say, well, you know, we were seeing about a 3% amplitude in this O2N2, this compositional variation, at about 30 degrees north, which is not where these tides are maximizing, right? They maximize near the equator. So maybe the variations are stronger near the equator. And maybe this is playing, you know, an appreciable role in perturbing that ionospheric density that we were seeing at the start. Okay. This is my last slide that I have. If you want to go get the data, there's a link with documentation on the instruments, algorithms, some PDFs describing the data files.
All right. Thank you, Scott, for a very interesting talk. Does anyone have any questions? You can either unmute and ask or type them in the chat and I can read them. And I will actually first ask a question myself for you, Scott. Has anyone you know, done any, I guess, modeling of how much the contribution from O+ would be? If you observe, say, the O+ separately, can you model how that would introduce the contamination?
Yeah, and this data set here probably gives us what we need, right? So if we're able to measure the O+ and we get a real nice altitude profile of it with the EUV instrument, computing radiative recombination brightness is not super hard. If you know the coefficients.
Mm-hmm.
And yeah, you could remove it and correct for this signal. Have we finished that? No. Are we working on it? Yes.
Okay.
I have a question. So does this whole process tell you how high up the actual dynamical tide propagates before all these other processes take over?
See if I have. Let me see if I included a plot. I put some in my backup. These. Oh no, I didn't. So we in the daytime hours, we can. What would be a good one? It's probably a good one. You know, if I see this kind of structure here, and I'll note this one goes to 200, which overlaps, you know, about a third the way up the other plot. These positive and negative alternating phase fronts, you know, these ones that you're seeing right down here at 110, you can follow them straight up to 300, which is about where our neutral observations end. And these are still, you know, they look pretty coherent. I have to do some PowerPoint magic to actually overlay them and convince you, but they line up really nicely. So you know, what you see is kind of an increasing vertical wavelength, right, as we get to these higher altitudes, which is, I guess anything with a short vertical wavelength is expected to have gone by here, and then increased diffusion and other things mean that we tend to see these signatures kind of become more vertical. But I'd argue we still see wind shears up here at 200 and something, even up to 300 kilometers over at least large scales.
So what you see is sort of a combination of local forcing at all altitudes plus the response to forcing from below or whatever.
Yeah, and you can try and pull that out. Look at the dominant wave numbers and things with each altitude, and that's something we're working on. A challenge is that in this altitude range, you know, in the middle thermosphere, you kind of have a gap at night. So you can look at dominant wave numbers, but you can't decompose the full tidal spectrum. You can do that at high altitude. You can do that down near the mesopause.
Okay, thank you.
And so, Scott, there's a question from Federico Gasparini, and he was wondering if you could say why you focused the wave 4 analysis on the ODAN2 30 degrees north instead of closer to the equator, where it tends to be lower.
Yeah, the contamination from O+ is worse and it starts earlier in the day. So when you look at these, that you don't get intelligible signals move. You could convince yourself they're moving up any direction you want. Is the short answer. So yeah, I tried to stay away from where the O+ is strongest, but stay near enough to the equator that D3, SE2 are still fairly strong. And the sweet spot seemed to be around about 25 to 35 north, somewhere in this region, which I guess I'm labeling as 30 degrees on these plots.
All right, thank you. Are there other questions?
Hi, Scott.
Hi, Wenbin.
Yeah, slide 32. Yeah, you have an amplitude of about 15 volume emission rate. How that compared to background? What percentage is the
Yeah, so I should have done. I have that on my to-do list. So it'll vary with time of day. But yeah, your mean value is maybe in the 400, 500 sort of range. So it's not tiny. It's not down at the 1% variation in the green line. We didn't build MIDI as an absolute photometric instrument, right? It's really trying to pull out Doppler shift. And brightness is something that we call it in the files, we call it relative brightness because we don't have a true absolute calibration of how bright is. You know, when we say it's 300, is it exactly 300? So I believe the perturbation is much more than those mean values. So I should really express this as a percentage and not as a photons per cubic centimeter per second. Yeah.
Okay, great. Thank you.
So Scott, there was another question from Han Lee. He asked that it seems the meridional component of DE3 is comparable with the zonal wind component, but they have a different seasonal dependence. How do you interpret that?
There's different modes of DE3, right? When you, I guess, look at the if you look at something like the Huff mode extensions, right, they usually fit a couple of modes to describe DE3. And you're right, the day of years when this stronger meridional wind is maximizing is not the days of year when the stronger zonal wind maybe quite as maximizing. And it's just it's sort of trade-off between which of these modes is more dominant and which one our analysis is picking up. If I went further, I'd repeat this whole thing in summer, right? When there's a long period, kind of July, August, September, when D3 is really strong as well. You need this combination of D3 to be there at some reasonable amplitude, and also you to be making the O2 and 2 measurements at the right latitudes at the right times of day and sort of things. And you can do it, but sometimes you can see with this, you know, there's a kind of a sliding window when it works, and then there'll be a sliding window that it doesn't work because at these latitudes we're not getting as complete coverage, and then it comes back a few days later.
And he had a bit of a follow-up question that does O2 and 2 respond more to the zonal or the meridional wind?
Vertical wind.
Okay, neither.
Which you can't measure. And likewise, I think this green line is responding to the vertical wind. I think it's right. It's right why, you know, the peaks and the troughs in the green line are lining up with the 0 points in the wind in the horizontal wind. In this case, but if they line up in the right places, then I can see the impact of it, even if I don't, you know, I can't look straight down and get a Doppler shift in the vertical direction. You're blinded by the Earth if you did.
Scott, I have a quick question.
Sure.
Which ion is the green line from?
Oh,
This is not my specialty, so I.
Knew someone would ask.
Is it an oxygen line or?
So it's an oxygen line. Go back. Here's 5 sources.
So it's a blended line. It's a line blended.
It's all about why do you get oxygen in this excited state in the daytime? And so different sources, you know, maximize at some of these different altitudes. So this 3-body bath type mechanism, that's what's producing this low altitude bright emission that stays through the night. This photo dissociation of O2 from things like Lyman beta, that's mostly in this lower altitude region, so that's why I'd crossed that one out. But I'm left with dissociative recombination of O2 plus photoelectron excitation of O, right, which would be right here in the, and then collisional deactivation of N2. So it's just not as simple a story. Now you can go run a model like GLOW and try and pull apart, you know, and say, yeah, what do I think is the dominant mechanism at each altitude at each time?
but from what I can tell, there's more than one thing producing the excited oxygen.
Thank you.
All right, does anyone have a last question? Seems maybe not. So, okay, thank you again, Scott. I think everyone enjoyed your talk. It was very interesting.
Thanks for giving me the opportunity. This was really good.
Awesome. Thank you, Scott.
Thanks.